Encryptions handle confidentiality. What about integrity? There is a man in the middle who want to modify the data, and we want to detect the modifications. For integrity, there are quite a number of cryptographic techniques are primitive, and now we handle one of them. We discuss one of them, which is the hash. What is a hash functions? A hash function is a program, okay, that take in the input of a arbitrary very long message. Okay, for example, it could be 7 GB movie, or it could be even just a 7 bytes strings. The output is fixed. For example, 256 bits. Okay. The output is known as a digest. Sometimes we call it checksum, hash, tag, hash value. Okay. The input is arbitrary, right? It can be very long, can be very short, but the output is fixed. Okay, 256 bits, 128 bits, or whatever, but it has to be fixed. There are many different types of hash functions. You may have heard of CRC checksum, and they are not cryptographic secure. They are hash function, but they are not cryptographically secure. Okay, we will mention what we mean by cryptographically secure later. Okay. Example of secure hashes are SHA-2. SHA-2 is a family of hash function that including SHA-224, SHA-256. SHA-224 means that the digest, the size of the digest is 224 bits. SHA-256 is 256 bits. And a more recent one is SHA-3. Okay, we can go to Wiki and see a comparison of all these well-known hash standard or hash functions. Let's look at one application of hash. And from there, we will understand the requirement, security requirement. So suppose Alice want to download Windows 7 from a website. Okay, want to download Windows 7 and install it. So Alice went to the website, okay, of Microsoft. As you can see on the right-hand side on the slide. Okay. So this website is legitimate, okay, because there is she look at the address bar, there is a padlock, there's padlock over here, and then the domain name Microsoft.com is displayed there. From these two, the padlock and the domain names, the correct domain names, Alice would be very sure that whatever display here is really coming from Microsoft.com. Okay. Then over here, there is a place for her to click to download the Windows 10. Okay, the 32-bit version or 64-bit version. When Alice click on this, a large file is being downloaded. Okay. This file quite often is stored in a third party. For example, it's not from Microsoft. Okay, it's from another parties. Okay. The website this secure website ensure that the link to the third party is secure, but the connection to the third party may not. There could be a situation that Alice did not actually download this file from the website. She may get it from some CD, right? She get it from some USB or whatever, some storage, someone passing this file. And now Alice will be concerned whether the file she has downloaded is legitimate, is a correct one. Could the file be modified by some third party so as to contain a malware? I guess we have this experience when we download games and so on, right? When we download games, download a file, when you store it, then we start to wonder, oh, Is the file downloaded correct one, legitimate? Would it contain the malware? So this website in Microsoft, okay, actually give us instruction how to check that. Okay, he give us instructions, okay, and essentially is what I described on the left-hand side. So this is a way to check. Okay. Suppose F is a downloaded file, or maybe getting from some USB or using get some CD. This is some file that we have obtained. And now download a tools. Download a tools is described here to compute the hash of F. Okay. Let's say that Alice has downloaded these tools and compute the hash of SHA-256. So the hash is some string, which is 256-bit strings. Okay, let's call it H. And next, visually confirm whether this hash, computer hash provided by the tools, is the same as the one displayed in the website over here. Okay. This website displays the SHA-256 digest of the downloaded file. The downloaded file have many different versions. For example, it could be Arabic, English, Chinese, different versions. So look at this one. Let's say you have Alice had downloaded Arabic 32 bits. Then this is the 256-bit digest. Okay, Alice compute the digest using the tools, and then visually compare whether these are the same. If it is the same, then accept that this file is authentic. If it is different, then reject. Fine. Okay. So there is a very large file, it's called a capital F, that Alice downloaded. And Alice is very concerned whether the downloaded one is correct. It may be modified during the transit when the downloading process. Someone which is a man in the middle modified the file. Or could be the file is already corrupted when it's at the storage, or when this file at least obtained from somewhere else, for example, from a CD-ROM or USB, and is coming from a malicious source. Okay, so this is a huge file. On the other hand, Alice have a secure means. He able to go to a legitimate website, very sure that whatever display in the website is correct. In particular, there is a digest display in the website. Okay. This digest is 256 bit. The file could be 7 GB. Okay. Now, Alice will download a tool, is compute the SHA-256 of this file, the hash of this file. This file is 7 GB. Compute and get a very short 256-bit hash. And then visually can compare whether this is the same as the one displayed in this legitimate website. Okay. So this is the way to verify it. And now let's think, suppose we are the attacker. Okay, so what would the attacker do? Let's put ourselves in the shoe of the attacker. We are the attacker. Okay, we control, somehow can influence the file F received by, downloaded by Alice. Okay, we are an attacker. Okay, we are a third party. We want to give Alice a malware. Okay, and we know that Alice is going to carry out this step to verify. Okay, right. This information in this website is public, right? We are very sure Alice is going to carry out this step. So what would we do? What would we do? Basically, from an attacker point of view, I want to write a malware. Okay, right now I'm an attacker. Okay, I want to write a malware and trick Alice to accept it. This malware should be, the hash of this malware should be exactly the same as the hash of the legitimate F. Right? If this malware, the hash, the digest of this malware is the same as the digest of F, then Alice will accept it. Is this possible? Yes, it's possible because malware is 7 GB, is very large, and the hash is very short. So it is possible that we have many different files having the same digest. Right, the digest is 256 bit, but the input could be very large, right? So there could be there are many possible files that have the same digest. Now, as an attacker, I want to find one that is same, whose digest is same as the file F, and yet is a malware. Okay. So now let's look at the problem faced by the attacker. The attacker actually want to do this. The attacker want to solve this problem. What is the problem? Given a file F, find another file M that's different such that the hash are the same. So we put ourselves in the shoe of attacker. We want to solve this problem. Okay, we want to write a program to solve this problem. Okay, so this program, this problem, okay, is posed to the attacker. Okay, and then from the attacker point of view, he's trying to solve the so-called second pre-image attacks. Okay, this is just a name. The second pre-image attacks is this: given F, find a M that is different from F, such that the digest of M is the same as digest of F. So this one problem faced by the attacker, this is the goal, right? This is the goal of the attacker. Okay. The goal attacker is this. What does the attacker have? In this case, attacker have a F. Okay, that's all. Okay, and the knowledge of the process. Right. There are many other similar problem requirement for the attacker, including something called collision attacks. I will omit the details. Okay, collision attacks is believed is much easier to be solved compared to second pre-image attacks. That means from the attacker point of view, second pre-image attacks is easier. The collision attacks is easier. Okay, I remember that previously I mentioned that when from the defender point of view, we want to design system so as to prevent attacker to meet the easiest goal, which is collision attacks. Okay. So here, let's consider a much more difficult problem for the attacker, which is second pre-image attacks. So if the hash is a CRC checksum, okay, it is very easy for the attacker to write a malware that match the hash. I will omit the detail because to do this, we have to understand how CRC checksum work. After you understand how CRC checksum work, it will be very easy to come up with this alternate malware M. Okay, but let's omit it because it's quite tedious to describe CRC checksum. And modern cryptographic hash are designed so that second pre-image attacks and collision attacks are very difficult to be carried out successfully. So attacker is unable to carry out second pre-image attacks and collision attacks. Okay. So things like SHA-2, SHA-3 is widely accepted to be secure in that sense. You may have heard of another hash function. In fact, in the online the website CyberChef, there are others hash function like MD5 and SHA1. These two are not secure. Successful attacks on second pre-image and collision have been demonstrated. Okay. So in this example, we assume Alice can get the correct digest from the website, right? If I go back here, yeah, this is a digest Alice can obtain. And Alice is very sure that this information displayed here are correct. Okay. What if Alice doesn't have this, doesn't have access to this one. Then the idea is similar to encryption. We introduce something called secret key. Okay. And allow me to omit the detail again. Okay. Primitive with secret key and achieve similar goal as the hash here are called message authentication code, MAC, or signatures. MAC is what we call using symmetric key, signature using public key. Because this is a demo in CyberChef, okay, then you can choose the hash function we want. You key in the input, then the output is a 256-bit digest. Over here, there's something for you to enter the number of rounds. This how many rounds SHA-1 use. The SHA-1 is a standard. He actually used 80 rounds. Okay. One thing to note here, okay, I keep mention that the digest length is 256 bit. Okay. So you'll be represented as 0, 1, 1, 1, 0, 1, 1, 1, and so on, right? A bit's binary sequence consists of only 0 and 1. But over here, it's displayed as this sequence. Similarly for the Microsoft website, right? So what is this about? This doesn't look like binary sequence. Okay. So the reason is that we know computer handle binary sequence bits, and every bit is either 1 or 0, right? It correspond to the circuit, whether there is is on or off. Okay. However, if we write it down, this one, 0-bit sequence as represented as 0 and 1, is very difficult for human to read, right? Imagine that in this website, then we have to list down 256 0 and 1s. So it's very difficult for Alice to verify it. Okay. So because of that, we typically we rewrite it, transform it to another form, okay, so that to help human to read the binary value. Okay, so we call this encoding. For example, the binary bit string can be encoded using 1 and 0 as shown here. As we can see, very difficult to read. Or we can write in hexadecimal form. Okay, so 5, 7, like this. Okay, each character here represent 4 bit. 4 bit, we can value 0, 1, 2, 3, 4, 5, 6, up to 15. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 is correspond value. Suppose we have value 1, 1, 0, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0, 1, 0, this is interpreted as 10, right? So how do we represent 10? We represent it as A, right? 11 as B, 12 as C, and 15 at F. Okay, so we have this form. Okay. And we can represent as base 64 and so on. Okay. So I leave the detail. You can easily Google these terms to understand, to see how to interpret how to transform from one encoding to another encoding. So here is that we want to display something so that easier for human to read. Likewise, the other way around. Okay. Suppose you have character A, B, C. Okay, we have to represent it in a binary form so that the computer can store it. Right? The computer handle binary. Yeah. So we have suppose we have a character A, B, C, or equal sign, question mark sign. So there's one way to do it is to use a standard called ASCII. So ASCII is a standard that lists down, okay, how we encode some readable character, English character, and common symbol. For example, A is encoded as this 8-bit sequence, okay, 010001. The hexadecimal is 41. You take the first 4 bits, so this is 4, last 4 bits, this is 1, and so on. The full table can be seen here. There are many such other type of encoding, especially when you handle non-English characters. Okay, against please you can go to the cyber chef to get more details. Okay, these are some demo. Okay,